Hello, everybody. This is Nafrit Sekho, and I welcome you on this platform, The Layers of Life Sciences, where we are discussing various aspects of life sciences in quite depth and detail, layer by layer. The objective is not just to help you in your graduation, post graduation, and competitive exams, including CSIR NET, but also to have a general discussion about the life processes happening around us. In the last 6 videos, we have thoroughly discussed the structures of monosaccharides. We have also discussed the stereoisomerism in case of monosaccharides. We have learned that learning few tips and tricks regarding their structures can help us to be comfortable with most of the structures of these monosaccharides. This much preparation is enough for you to be confident while answering the questions. And I hope you will sail through all the questions wherever your knowledge is being tested directly. Now, what do I mean by knowledge being tested directly? It means where the simple questions are asked from you. For example, what is the difference between aldoses and ketoses? What is the difference between pyranose or the furanose rings? Draw the structure of glucose or draw the structure of fructose. What is the difference between epimers or enantiomers? Now, you can, when the questions are that direct, you will sail through all these questions and you will be able to attempt all these questions with quite confidence. But I know that this confidence may shatter a bit when your knowledge is being tested indirectly. Your knowledge is tested indirectly when the questions which are asked are the analytical question. Here in Canada, I have come across so many students who just don't get lost while doing such questions. They are scared, literally scared of such questions. It is again my responsibility to make you comfortable with all such questions as well. CSIR NET is also the exam which, if you want to clear, you need to be comfortable with the analytical questions because whole of the part C is composed of such questions. Now, I am giving some tips that how to deal with such questions, how to approach such questions. They are never difficult. Instead of being scared of them, you should be enjoying doing such questions because they actually really test our knowledge that how thoroughly we have done our homework. Now, the first thing is you should be confident about your preparation. You should be confident about your basic knowledge. That is point number one. This is the first step. While reading the questions, most of the students lose their confidence. They feel that, okay, we did everything, but this question, no, we don't know from which part it has just come up. So there the confidence shatters and they just lose the confidence and their ability to think about the question as well. So that is the first place where most of the students slip. So first of all, don't lose the confidence. You should be knowing that you have prepared your topic thoroughly. Number 1 point. Number 2 point, treat these questions as riddles. As in riddles, what we do is that we apply our basic knowledge and then connect the dots. Based upon that basic knowledge, we connect the dots. Here also you need to do this. No matter how out of the word that question appears to be, and try to apply that basic knowledge to solve that problem. That is the point number 2. I am doing few analytical questions over here. My objective of doing these analytical questions for you is not to tell you, okay, these are the type of the questions which will be asked in your exams, or this is how you need to do these questions, this is how to find the answer of this particular question. Because analytical questions, nobody knows from which portion what kind of question is asked. Nobody can claim that. Over here, I can just tell you how to approach such questions, how to deal with such questions. So here, for that, I am just taking few examples, that all these are the questions where your knowledge is not being tested directly. Some twist is there in the question. You need to deal by holding your nerves, by believing in yourself and your preparation. So let's start with the first question. So first of all, let's read this first question. In monosaccharide derivatives known as the sugar alcohols, we have done sugar alcohols, the carbonyl oxygen is reduced to hydroxyl group. Yes. For example, D-glyceraldehyde can be reduced to glycerol. However, this alcohol is no longer designated as D or L. Why? Now, if you are giving any CSIR exam, they will give four options after that, but basic remains the same. So how we define D and L forms, the basic lies there. How we define D and L forms? We defined DLL forms as that we need to look at the orientation of OH group. The orientation of OH, if this is the carbonyl group, and this is, for example, this is the chiral, this is the terminal carbon, right? So what is the D and L form? D and L form is defined as that we need to look for the orientation of the OH group on the chiral carbon, which is the farthest from the carbonyl group. This is the chiral carbon, which is the farthest from the carbonyl group. Then if OH is present on this side, it will be D form. And if this OH is present on this side, this will be the L form. Now, answer lies in the question only. They are saying this carbonyl group, this carbonyl oxygen is reduced to hydroxyl group. This is reduced to, we did it, right? There is a reduction. This is actually eliminated from here. Now, by definition, D is that D or L forms are that we need to look at the orientation on the carbon which is the farthest from the carbonyl group. Now, even carbonyl group is not there. The basic group on which the definition lies, that group is not there. How we can define these alcohol derivatives in that case? Now, this on this carbon, now there is no carbonyl group, there is the OH group. Now, by the definition, how we can just name it as D or the L alcohol? We cannot, because in the definition of D and L orientation, there is carbonyl group. If the carbonyl group is not there, we cannot designate these alcohols as D or L. Very simple. Very simple. Even if you have not done the derivatives, although we have done in detail, in your books, it is not in that detail. Even you have not done these in that detail, then also you can answer this question. Then also you can answer this question just by knowing the definition of D and the L form. You need to know that the definition of the D and the L forms is based upon the presence of carbonyl group in the molecule. If the carbonyl group is not there, you cannot designate that molecule as D and L, which happens when any monosaccharide is actually converted into the sugar alcohols. Now, next question. I will do few questions. You will actually notice that they seem to be really hard, but they actually are not. They're actually not. So let's go over here. This is another question which I have taken from the book, The Principles of Biochemistry, Leninger's Principles of Biochemistry, written by Nelson and Cox. So this derivative we haven't even done, right? Let's see what they are saying. Many carbohydrates react with phenylhydrazine to form bright yellow crystalline derivatives known as osazones. Yes. Now, Because we have not done it, most of the students will read this. They will say, oh, we have not done, so we don't want to even look at this question. That is the biggest problem with the analytical questions. You cannot do each and everything. Analytical questions will always be coming out something which we have not done. We need to read the question. We need to have confidence on whatever we have done, right? Just read that question with that kind of devotion and dedication that I have prepared everything, I have done everything related to it. Now let me see what this is the riddle again. This is the riddle. We have not done this part, but still we can easily do that. Believe me, we can. You just need to read this whole question. All the hints, everything is there in this question only. It is existing in this question only. So let's read it once again. Many carbohydrates react with phenylhydrazine to form bright yellow crystalline derivatives known as osazones, right? So they have given this a reaction over here. Now, what they are saying, so you can see the reaction. You can see what kind of, okay, carbonyl group is losing, right? Is being lost, and some carbon number 1 and 2 are kind of similar, right? Rest everything is same. This is everything is given in the question. You just look at the structures. Now, let's go. The melting temperatures of these derivatives are easily determined and are characteristic for each OSA zone. This information was used to help identify monosaccharides before the development of HPLC or glass liquid chromatography. Listed below are the melting points of some aldose OSA zone derivatives. So here, these are the melting points, right? As the table shows, certain pairs of derivatives have the same melting points, although the underived monosaccharides do not. Why do glucose and mannose and galactose and talose form osazone derivatives with the same melting points? Okay. So glucose and mannose form the same melting points. They are saying, okay. Now this is the answer over here lies in their structure. Glucose. That's why I tell you that the video Biochemistry 2 is really important. It's really important. There I have given you the trick that how every structure can be kept in your mind, how it can be retained in your mind. So for glucose, the code is 245, right? 245, right? Yes. For mannose, the code is 45. For galactose, the code is 25. And talose, the code is 5. So now what the codes are telling? The codes are telling us the position of OH, which means on position 2, 4, and 5 in D-glucose, OH should be should be present on the right-hand side of the carbon skeleton. But in mannose, apart from position 2, just on 4, 5, it should be present on the right-hand side. In galactose, on position 2 and 5, it should be present on the right hand side, while in talose, it should be present on just on the 5th position. Now, we know that when these osazones are formed, then OH group and this carbonyl group, all the modifications happen on either on carbon number 1 or carbon number 2. So when this modification will happen in glucose and in case of mannose, then ultimately this carbon number 2 will get modified. Here also in mannose also it will get modified. So OH, the difference is just in they are the epimers basically, right? The position difference is just on the position number 2. That's why these two are epimers. Now, after modification, the position number 2 will not matter. It will, the hydroxyl from this, the hydroxyl group from this carbon will get eliminated. It means the derivative of glucose and mannose will actually be the same. Will actually be the same, right? And same is the case with the galactose and this talose. Again, over here in galactose, there is a hydroxyl group on carbon number 2 will get eliminated. And when it will get eliminated, then this orientation will not matter. So no difference on this carbon number. So just carbon number 5 on both of them, this structure will be formed, and just on carbon number 5, OH will be directing towards the right hand side. So this, whether glucose is taken from over here or mannose is taken over here, the structure, the resultant structure in both of them will be the same, this one. That's why the melting temperatures of both the derivatives of both of them will be same after reacting with this phenylhydrazine. And same is the case with galactose and talose, right? There, this OH will also go over here, and just on carbon number 5, OH will be directing towards the right. So that will, this will be the case for galactose and talose. So that's why again their melting temperatures, although before undergoing this process they were different. These two are epimers of each other, but they are different, right? Again, these are also two different things. But after this modification takes place, then the resultant is is same for epimers. It is actually the case that all the epimers which are depending upon the position, second position, they all become same after this modification. That's why their melting temperatures are same. So, till now, the two questions which we have done over there, our biochemical or the chemical knowledge has sufficed the purpose, right? But sometimes we may have to learn few skills which do not belong to biochemistry or chemistry for that matter, but to mathematics or statistics, or we can say to physics. When we will be doing instrumentation, we will have to learn so many concepts of physics. Now, when we will be doing genetics, over there we will have to learn so many mathematical concepts. Without going into binomial theorem, you will not be able to solve the questions of the genetics. So over there, we will have to learn the binomial theorem. So here also, at the end of this topic, which is the structure of monosaccharides, I will love to introduce you to another concept of statistics. The concept is average. We know how to find the mean or an average of any data. So the same concept will be used. So first of all, let's read the question, and then let's learn how to apply the concept of some another sphere over here in biochemistry. So first of all, let me read the question. The question says, a solution of one stereoisomer of a given monosaccharide rotates plane polarized light to the left, that is counterclockwise, and is called levorotatory isomer, designated as negative. The other stereoisomer rotates the plane polarized light to the same extent but to the right, that is clockwise, and is called dextrorotatory isomer, designated as positive. An equimolar mixture of positive and negative forms does not rotate plane polarized light. The optical activity of a stereoisomer is expressed quantitatively by its optical rotation, the number of degrees by which plane polarized light is rotated on passage through a given path length of a solution of the compound at a given concentration. The specific rotation of an optically active compound is defined as observed optical rotation in degrees divided by optical path length in decimeters multiplied by concentration in form of grams per ml. The temperature and wavelength of the light employed, usually the D line of sodium, that is 589 nanometers, must be specified in the definition, the way it is specified over here. Now, a freshly prepared solution of alpha-D-glucose shows a specific rotation of positive 112 degrees. Over time, the rotation of the solution gradually decreases and reaches an equilibrium value corresponding to the optical rotation, specific optical rotation equal to positive 52.5 degrees. In contrast, a freshly prepared solution of beta-D-glucose has a specific rotation of positive 19 degrees. The rotation of this solution increases over time to the same equilibrium value as that shown by the alpha anomal. Draw the Howard projection perspective formula of alpha and beta forms of glucose. What feature distinguishes the two forms? Number two is, why does specific rotation of a freshly prepared solution of alpha form gradually decreases with time? Why do solutions of alpha and beta forms reach the same specific rotation at equilibrium? Third part is, calculate the percentage of each of the two forms of D-glucose present at equilibrium. Now, if you see this question, then you will realize that whole of this part with which the question starts, like till this point, it is like, with respect to these three questions over here, this is quite irrelevant. And it is actually irrelevant because here we are talking about glucose. It's both the stereoisomers rotate the plane polarized light towards right hand side, or we can say clockwise, right? And both are dextrorotatory. But here in the introduction, they are talking about any compound whose two isomers are designated as positive and negative because they rotate the plane polarized light first to the same degree, right, and to the opposite direction. In the case of D-glucose, both the stereoisomers, first of all, do not rotate plane polarized light to the same degree. They are rotating to two different degrees. One is rotating to 112 degrees and another one is rotating it to 19 degrees, right? So first of all, this is the difference. And then secondly, here it has been rotated by both the stereoisomers in the same direction. Here, whatever they are talking about, there the rotation is towards two different directions. So this thing over here is quite irrelevant with respect to the subject matter of the question. So why the examiner will do this thing over here? Now, generally, as I discussed in the introduction, students are afraid of reading the long questions. Everything which is mentioned over here, you will not come across this while going through your biochemistry books, right? It will be something new for you. And actually, introduction of something new to you will discourage you to read the question and to give you the feeling that you don't know the answer, whatever this question is about, you have not even read about it. So this will discourage you. So here, this is kind of the psychological trick which examiner may play with you. And secondly, just to confuse you. So all the kinds of irrelevant information is given over here, although whatever compound is being talked in this first paragraph is totally from this alpha D glucose and beta D glucose, right? So this is just to confuse you. Here you need to just filter out all the irrelevant things. And now we can always filter out the irrelevant things if we have the confidence in ourselves, if we have confidence in our preparation. So we are ignoring whole of this thing. Then let's come to the question. We have done this part, right? in the video Biochemistry 4, we have done mutarotation at the end of that video. We know about this thing, right? And because we have done this, so now you can easily draw the Howard projection formula, because we have drawn it in the video Biochemistry 3. This part also we have covered, that why the final value comes out to be always 52.5 degrees. We have done it in mutarotation, right? This question you can easily answer if you have watched the video Biochemistry 3, and this can easily be answered if you have done the video Biochemistry 4. Now, let's come to this question. Calculate the percentage of the two forms of D-glucose. Now, in case of glucose, even in the video Biochemistry 4, at the end of that, we have done that at the point where equilibrium mixture is formed, then 1/3 of that is alpha, and 2/3 of the solution is beta. Many books have also given it even in the form of percentage. When you will be doing this, then you may already be knowing that what is the percentage of alpha and beta forms in the equilibrium mixture of D-glucose. But same kind of question can be asked for galactose, for mannose, for fructose, for any monosaccharide, and you cannot learn the composition of each and every equilibrium mixture. So it is always good to learn that how to calculate. If here in the question they have given the individual optical rotations, and they have given the optical rotation of the resultant equilibrium mixture. This is actually the optical rotation of the resultant equilibrium mixture. So now if the individual optical rotations are given and optical rotation of resultant equilibrium mixture is given, then how to calculate the composition? So here we need to learn that. And to learn that, we need to just go back to mathematics. So let me, or we can say statistics basically, because mean and average is a very basic concept of stats. So for example, there is some data set. For example, it is 10, 12, 10, 16, 10, and 12. So this kind of data set is there, and you are asked to find the average of it. So one way of finding the average is that you may add all the values, 10 plus 12 plus 10 plus 16 plus 10 plus 12, right? And divide it with the total number of entries in the data set. So how many entries are there? They are 1, 2, 3, 4, 5, 6. 6 entries are there. You divide, you add it, and you divide it. You will be able to find the mean of this data set. Another way of finding the mean is that first of all, we find the frequencies of different entries within the data set. So for example, the frequency of 10 over here is 3, because 10 in this data set comes thrice. We can say the frequency of 10 is 3. So rather than adding 10 plus 10 plus 10, I can write the frequency. So 3 times 10 is actually 10 plus 10 plus 10 only, right? So we're here, this is the frequency, and this is our data entry. So same is the case, same we can do with 12. The frequency of 12 is 2, right? And the frequency of 16 is just 1, right? So 16 is just 1. Now, the total of the frequencies over here will give me the total number of entries within that data set. So I will add these frequencies, 3 plus 2 plus 1, which will be equal to 6, right? So in this way, we can find our mean. This is also the way to find the mean. When we actually apply the frequencies to find the mean, then that mean is actually called, or we can say that average is actually called weighted average. This is called weighted average. So same kind of formula we will be applying over here. So let me write a general, very simple general formula over here. How I can mention this weighted average. So it is, what is the frequency? Let it be the weight of it, right? And this is my entry number one, x1, right? Plus weight 1. Weight 2 multiplied by x2. Weight 3, right? That is the frequency of the third, and x3, right? So this is generally in stats, it is a submission is written, and it is written as wx, submission of wx, right? So here I'm trying to just keep the things very simple. So here, then after that, to find the average, we need to have the total entries. So in the total entries, we will do W1, W2, and W3, right? So here we will add all the weights of all the entries, right? Or we can say frequencies of all the entries. So this same thing is written over here in the generalized form. So we are gonna use this formula for calculating our percentage of the composition of different stereoisomers in the equilibrium mixture. So how we can do over here? So we know that at equilibrium, the composition of equilibrium mixture is such that it is composed of either alpha or beta isomer of D-glucose, because the concentration of the linear structure and the furanose forms of glucose, all three of them are just very negligible. So practically, equilibrium mixture is composed of alpha form of the pyranose ring or the beta form of the pyranose ring. So the final mixture is composed of alpha or beta. These forms are there. Now, we know that the optical activity of the alpha form is positive 112 degrees. And the optical activity of beta form is positive 19 degrees. And that of resultant mixture, where alpha and beta both are present, when this alpha and beta form both are existing, then the optical activity of that resultant mixture is 52.5 degrees. So now, if over here I may increase the amount of alpha, then the value of this optical activity of the resultant equilibrium mixture will increase, right? It will increase for a while before again coming back to 52.5 degrees, and it will go closer to 112 degrees. Similarly, I may increase the amount of beta stereoisomer over here. Then in that case, the value of optical activity of the resultant equilibrium mixture over here will decrease, and it will go closer to the 19 degrees. It means whatever amount of alpha and beta forms are there, that amount is actually affecting the resultant optical activity. So it means we can find the optical activity of the resultant equilibrium mixture if we just add 112 and 19. How many molecules are present which are having the optical activity of 112 degrees? That matters. So all the alpha, whatever the amount of alpha isomer is present, those are causing the optical activity of 112 degrees, while whatever amount of beta isomer is present, that is leading to the optical activity of 19 degrees. And when they both interact with each other, then the optical activity of 52.5 degrees is formed. But this is actually the case of weighted average. So over here, this is the frequency of 112, and this is the frequency of 19 degrees. Now we need to add the frequencies. So it is A plus amount of alpha plus beta. So we have actually applied the same thing over here, this same thing. So this is the frequency, this is the data entry, the optical activity. Then this is the frequency of the data entry with 19 degrees, right? So, and we have added the frequencies and we will find the resultant optical activity due to the presence of this much amount of stereoisomers with 112 degrees of optical activity and these much of beta stereoisomers with this much of the optical activity, and then we need to find the average of them by dividing with the total number of total amount of the stereoisomers present, be it alpha, be it beta. So now, this much is the application of a concept. Now we need to do the simple mathematical calculations. So in all these questions where we need to find the final composition, as over here we need to find the final composition in terms of percentage. So what we can do, let that alpha plus beta stereoisomers are forming 100 ml of our resultant equilibrium mixture, right? Now, after this, we will let another thing. Let alpha is equal to x, right? Now, from the same equation, if alpha is x, right, then beta will be equal to 100 minus x. Now, so putting these two values, this value of alpha over here, this alpha is equal to x, putting that value over here, and the value of beta over here, we can create an equation. This is the thing. So I am putting the values over here, just putting the values. So alpha is equal to x, so I will write x 112 plus beta, value of beta is 100 minus x, right? So 100 minus x, and then this value 19, right? Now that alpha plus beta is equal to 100, so I can put 100 alpha plus, I can put 100 over here, and then it is equal to 52.5. Right now, just this calculation. So it is 112x plus 1900 minus 19x divided by 100 is equal to 52.5. Now over here, these two values are with the same variable, that is x, so we can actually just deal with these. 112 minus 19 will come out to be 93x, right? So 93x plus 1900 divided by 100 is equal to 52.5, right? Then next, taking this 100 over here and multiplying with it, right? So if I will take 100, here it is in the division, on the other side it will multiply. This side we need to multiply it with 100 because here it was in division, on other side of is equal to sign, it needs to multiply. So 93x plus 1900 is equal to 5250, right? Now this 1900 will go on the other side, so it will form 93x is equal to 5250 minus 1900. So which comes out to be 93x is equal to 3350 equal to 3350. So X will be equal to 3350 divided by 93. So what will be the answer? 36.02. So X is equal to 36.02%, which means alpha is equal to 36 point. So X is equal to alpha, right? So alpha is equal to 36.2%. Now beta is equal to 100 minus X, right? 100 minus X. So 100 minus X is equal to 100 minus 36.02. The answer will be equal to 63.98%, right? So this beta is equal to 63.98% and alpha is equal to 36.02% in the equilibrium mixture of the beta D glucose. So this is the composition for the beta D glucose. That is the equilibrium mixture of the beta D glucose, right? When its optical activity is 52.5 degrees. So due to the presence of 36.02% of alpha and 63.98% of beta, the resultant optical activity is 52.5 degrees. So this is about glucose. Same kind of question can be asked for
other
they
monosaccharides.
may give the amount of alpha present, they may provide the amount of beta present, and they may also provide the values of their individual optical activities, and we may have to find the resultant optical activity. There also you will apply the same formula, same method, right? Same this concept of weighted average. You will write the amount, you will put the amount of alpha. For example, we need to find the value. So alpha is 36.02. You will put this value, multiply it with 112 plus 63.98, multiply it with 19, right? And then divide it with 100, and you will get this. By doing this, you will certainly get this answer of the final optical activity. So they may actually keep the final activity to themselves. So this is another kind of concept which I thought you should be knowing. It is not at all difficult. Yeah, some mathematical portion is there, some mathematical calculations are there. With this, I am winding up structure of monosaccharides. I hope now you must be really, really comfortable with this topic and you will do wonders in your exams regarding that. I wish you all the best. I will see you in the next video with our next topic, that is the structure of oligosaccharides. In that, we will be discussing the structure of most important oligosaccharides, that is disaccharides. So till then, goodbye. See you in the next video next week. And till then, take good care of yourself.